Good morning, trig and precalc fans. How we doing on this fine Tuesday morning? A little cloudy, a little rainy last night. Got a little bit of water coming out of the sky last night. Hope everything's going well for you and your family. Hope everything's going well in your household. Today we are venturing in to the last day. The last day of material for the year. It's such a sad day. The last day of having to listen to me on a YouTube video. I know you're dabbing tears from your eyes at that point. The last day of having to do any type of homework or anything like that. What we will do from this point is we'll have a day of review tomorrow, and then we'll have an evaluation on Thursday, like we've done the past couple weeks. Once again, I apologize for yesterday. I don't know what with the video was the issue with the video that we had, but it was awful bright. I put a second video on there. Hopefully that was a little bit better for you, and for you to be able to view the video. But this will be the last material that we will cover in trig and also in precalc this year. We are done, QED. Today what we're going to work on is we're going to work on the conversion of polar coordinates to Cartesian coordinates, and the XY system to the R theta system, or the R theta system into the XY system. Because there is a direct relationship between those two, we need to be able to convert from one to the other. Because sometimes it's easier dealing with things in polar coordinates, sometimes it's easier to deal with in Cartesian coordinates. If I'm going to graph a line y equals 2x plus 3, that's a lot easier in Cartesian. But if I'm dealing with a cardioid, or if I'm dealing with a lemacon with or without a loop, or 3-leaf, 4-leaf rows, the cardioids, that's a little bit easier in a polar coordinate system. So there's benefits to both of them, and you need to be able to utilize, once again, as I talked about yesterday, a lot of graphics occur, especially the old school computer graphics that we used to do with pictures. I used to have polar coordinate systems. So if you're programming something in regards to the polar, or into graphics at that point, basically you're dealing with polar coordinate systems. So what we're going to work on today is we're going to pick a point, and it does not matter which point we pick. If we pick this point, we have the x and the y axis here. But we also have the r's and the theta axis. So we have two different types of axes here. So this point that we put up here can be labeled as xy, or this point that we put up here could be put up here as r and theta. Okay, so we could have either points at this point. There we go, that's a little bit better. Get you a little bit closer. Sorry about that. So this point up here could be xy, or it could be r theta. Does not matter which one we utilize. Well, if I'm taking a look, how we determined xy was we would venture out to here, and then we would move up to here. This would be our x value, this would be our y value. So we have the x value and we have the y value there. The other way of dealing with this is I go out x, up y, and get to this point. I can rotate the value of theta and move out a distance of r. So my distance from this point to this point is the length of r, and I've rotated my value of theta. Okay, so we have two different ways, once again, of being able to tell what we have here. Is it r theta, or is it x and y? Let me move this just a little bit more. There we go. That's a little bit better. Now you can maybe see it a little bit better. So we have r theta and we have xy. Now, if we take a look at the x and y, here's my x, here's my y. Well, what does this form? What type of angle does this form? If I go out x and vertically y, what type of angle is that? That is correct. That is a right angle. That is a right angle. And if I look at what we have here, we can take a look at this distance out to here is a value of r. And what we create is a nice little handy dandy right triangle. So we have a right triangle. So if we have a right triangle, we have some relationships that we can use with respect to a right triangle. Taking a look at this triangle that we have here and that we formed, what is the value, what would be the ratio of the cosine of theta? Well, if I take a look at this triangle, cosine is defined to us as adjacent over a hypotenuse. So we have x over r. And if I multiply both sides by r, we have x is equal to r cosine of theta, which allows us to convert our polar coordinate into a Cartesian coordinate. Cartesian means x and y. Polar is r and theta. Or we have a relationship that takes cosine of theta as x over r. Now if we take a look at the sine of theta, we look at our triangle up above. What is the sine of theta defined to us as? Well, that would be y over r. And once again, we can multiply both sides by the value of r, using our multiplication property of equality. So we would have y is equal to r sine of theta. Once again, this gives us a relationship that allows us to take a polar coordinate, r and theta, and move it into a y value. So if I know r and theta, I can find an x and y value. The tangent of theta, we may use this, is equal to y over x. And this is once again a relationship that we may utilize to convert. Then we have our good old buddy Pythagoras. Oh, where you at, buddy? There you are. We have our good old buddy Pythagoras. And if I take a look at my good old buddy Pythagoras up here, what would my good old buddy Pythagoras say about this triangle? Well, he would say x squared plus y squared is equal to r squared. So this gives us once again a relationship between r and x and y. And if I need to, which I probably will, this also allows us to say r is equal to the square root of x squared plus y squared. So if I needed an r or r squared, I have both relationships there. Alright, what we're going to do is we're going to convert r sine theta, or r equals 6 sine of theta, into a Cartesian coordinate system. We are in r's and thetas, and we want to convert them back to x and y's. We want to convert it back to x and y's. Well, if I take a look, my sine of theta from up above is defined to us as y over r. What this does is this gets rid of my sine of theta and gets me a variable y. But we added a variable of r also to this. So I want to get rid of my r somehow. Well, r is equal to the square root of x squared plus y squared, but that's sort of ugly to deal with, so I'm going to wait. Because if I multiply both sides of my equation by r, we are left with r squared is equal to 6y. And looking up at what we have for r squared is equal to 6, or r squared is equal to x squared plus y squared. Putting in my substitution, I have x squared plus y squared is equal to 6y. Now typically what we do with this is we put this into a standard form, which means equal to 0. So we can subtract our 6y over. So we have x squared plus y squared minus 6y is equal to the value of 0. If we follow the same method of madness up here with the r equals 4 cosine of theta, r equals 4 cosine of theta, we have, let's see, r is equal to 4 times the cosine, which is x over r. And we can multiply both sides by my value of r once again. So we have r squared is equal to 4x. And then make the same substitution, r squared is equal to x squared plus y squared. So we have x squared plus y squared is equal to 4x. Or x squared plus y squared minus 4x is equal to the 0. Which are both our equations of circles. Now if you take a look at the equation of the circle, what would be easier to deal with? Would this be easier to work with, or would this be easier to work with? That's a thinker. Let's take a look down here. We have a fraction, and dealing with fractions is sort of difficult. So what I'm going to suggest that you do is multiply both sides by 3 minus cosine of theta. So we're left with r times 3 minus cosine of theta is equal to the value of 5. Now if we take a look at this cosine of theta once again is equal to x over r. So we have r 3 minus x over r is equal to the value of 5. Using our distributive property, we're left with 3r minus x is equal to the value of 5. Which gets rid of the cosine, gets rid of this r here, but I still have an r here. Well, how do I deal with that? Well, let's isolate it. So we have this add our x to both sides. So we have x plus 5 is equal to 3 times, well, what is our value of r? Well, if I had r squared is equal to the square root of x squared plus y squared. But now I only have r, so what I have to do is I have to take that radical into my problem. Ew. But we got to do it. So we have the square root of x squared plus y squared. Now what I'm going to ask you to do is I'm going to ask you to use your algebraic skills to be able to get rid of this radical. This is multiplication. What do we have to do to both sides to get rid of the square root? We have to square them. So if we square one side, we have to square the other side. Now the nice thing about on the left-hand side, we have multiplication here. So we can distribute this over both of our terms. So we have 3 squared times square root of x squared plus y squared squared. On the right-hand side, we don't have that luxury because we have addition in there. So what we have to do is we have to FOIL this out, which is x plus 5 times x plus 5. So what we are left with is we're left with 9 x squared plus y squared is equal to, now we have to FOIL this out, x squared plus 10x plus 25. Remember, we can't just square both of our terms. We have to FOIL this out. So now we have to get into standard form, which means get all your variables on one side and the numbers on the other side. So we have 9x squared plus 9y squared is equal to x squared plus 10x plus 25. We can subtract off our x squared and our 10x. So what we're left with is 8x squared plus 9y squared minus 10x is equal to the value of 25. The other problem I'll leave for you to do, but it's basically following the same thing we just did right there. Okay, so if you follow along with what we did there, it is the exact same process. Over there, we're gonna multiply both sides by 3 minus 5, or 5. Ugh. We're gonna multiply by 3 minus sine of theta, 3 minus sine of theta. We could sub in y over r for this. We could distribute our r over. Those would cancel, and it's going to be the same simplification at that point. We can convert the other way. I don't know what happened to my last page. If I had x squared plus y squared is equal to the value of 25. And I want to put this into a polar coordinate system. Well, if I look x squared plus y squared, we are x and y, we want to go to r's and thetas. X squared plus y squared is equal to r squared. So we have r squared is equal to 25. Typically, when we solve for polar equations, their solutions are going to be r equals or r squared. So we have r squared is equal to or r is equal to. So this would be acceptable in regards to a solution, but we could take the square root of both sides, say r is equal to 5. R is equal to a value of 5. Basically what this is a circle with center point at the pole with a radius of 5. No matter what value of theta I put in there, my r value is going to be a value of 5. So what we get is we get a circle with center point at the pole. So this is conversions of polars. If I take a look at one last problem. Sorry about this. If I look at one last problem. Let's see, x squared plus y squared plus 2x is equal to a value of 0. We take a look at this problem very quickly. Once again, the x squared plus y squared gives us r squared. But x, we don't have anything that we can deal with the x. So x is equal to r cosine of theta. So we have 2 times r cosine of theta is equal to 0. And once again, we could solve for our value of r squared. But if we could subtract off the 2r cosine of theta. So we have r squared is equal to negative 2r cosine of theta. We can divide both sides by r. So we're left with r is equal to 2 cosine of theta, negative 2 cosine of theta. So that is conversion back into a Cartesian coordinate system. You should now be able to do the back side of the worksheet I gave you yesterday. Once again, the front side was just graphing the polar coordinates. Back side here is conversions of Cartesian to polar, polar Cartesian. Please work on that today. The solutions, the solutions are there from yesterday, so you can be able to deal with the solutions. Tomorrow I will post a review sheet. And once again, Thursday will be the last evaluation that we will have this year. Other than that, I have nothing else for you. Hope once again everything's going well for you. If you do have any questions, feel free to comment me. I'll help out as best as possible to be able to get you through the last week of material. Other than that, I miss you guys. Wish we were sitting in class once again, enjoying our last few days together, but yeah. It's okay. It's all right. Other than that, I have nothing else for you. Adios. Have a great day.